A lot of announcements for you guys this week too. So this week we will be doing experiment 4 in lab. If all goes well with experiment 4, it takes about 4 hours or so. So you will potentially have time to complete your recrystallization from experiment 3 or work on melting points from experiment 3. So if you don't complete those things during lab this week, then you'll definitely need to do that in open lab, because if you look down here next week, your experiment 3 report is due in lab next week. Okay. Your experiment 2 worksheets are due this week, so make sure you have those completed, the computer modeling, the physical models, and have your menthol and your morphine printouts also attached to those worksheets. Make sure you bring calculators to lab this week and every week. There's always a possibility that there's going to be numbers on the quiz, and there's always a chance that you need to calculate things in lab as well. So bring your calculators. And so we will have quiz number 4 this week. You should get experiment 1 report back from your lab prof very soon, if not already. So make sure you look at the feedback on that for future reports. And reminder that, again, experiment 3 report is due next week. Then for Friday, the 4th of October, so not this Friday, but the following Friday, Open Lab is going to close at 12 p.m. because of the President's inauguration. All classes are going to end at 12 p.m. and there aren't going to be any afternoon classes that Friday. And so that means that Open Lab as well will be closing at noon on Friday, October 4th. Okay, this week we are going to be using a distillation you're going to get an unknown that's going to be comprised of multiple things. You'll have to separate it and then characterize and figure out what you have. And I'll talk about the specifics on the unknowns here in a little bit. But what we are going to be using is what is called a fractional distillation. So I want to discuss the differences between a simple distillation, which is something you've already used, and a fractional distillation. Okay, with a simple distillation, and we've used this twice, once for taking the hexene off of your unknown from experiment 1, and once for removing the ether from your trimeristin in experiment 3. It is used for separating a volatile from a non-volatile compound. So you need a really large difference in boiling points for a simple distillation to work. You want at least your boiling point or the difference in the boiling points between these two components to be at least 100 degrees different. So you need a very large difference in order to make that work. And so, like, with experiment 1, your neutral compound and the hexane, your neutral compound's boiling point, not melting point, but boiling point, was much, much greater than hexane. And so that's why it worked. Same with trimeristin. The boiling point of trimeristin was much, much greater than ether. So that's why it worked in experiment 3. With a fractional distillation, you can distill components that have a 20-degree difference in temperature and separate them. And so what is involved in a fractional distillation is it's actually a series of simple distillations, all in one apparatus. And so we use a term called theoretical plates, and I'll tell you where that comes from here in a little bit. But the number of theoretical plates is equal to the number of simple distillations that are carried out in this one apparatus. And so that gives you how many simple distillations are done. So this idea of theoretical plates came from when they first were doing fractional distillation. What they would use is a column that would actually have plates in it. And so in this column, as you went to distill something, you would have all these mini simple distillations taking place. Vaporization, and then condensation, vaporization, condensation, vaporization, condensation, all the way up. And that is how many mini simple distillations you would do, is equal to this number of plates. So that's where theoretical plates came from when you're talking about doing a fractional distillation. And so today, in a regular lab setting, columns like this aren't used so much, but in industry, this is still used if a fractional distillation is needed. They make a large column with all these plates in there for the fractional distillation, okay? And so before, when we were taking off the ether, taking out the hexane, we were doing one simple distillation. That was it. If you, to your simple distillation apparatus, were to just add a vertical column, so not any packing or anything, just add a vertical condenser, that will add about 2 to 3 theoretical plates. Now, if we pack that condenser, which is what we're going to do this week, the packed vertical condenser can add 5 to 6 theoretical plates. And so that's what you will be adding to your, instead of just having a simple distillation, you will be adding about 5 to 6 theoretical plates. And so if we look at this more in terms of physical chemistry approach, in your lab manual, there's a lot of discussion about Raoult's law and looking at vapor pressure of a single liquid in comparison to the vapor pressure of the overall mixture of liquids and how that's related to mole fractions. So I'd look that information over. This is kind of a summary of that and how things are related. So if we look at this phase diagram, we've got a vapor and a liquid. So we're looking at the distillation of this liquid that's made up of octane and hexane, and what happens on the liquid side and what happens on the vapor side, okay? So this side of the phase diagram is the liquid side, this side of the phase diagram is the vapor side, okay? So say we take this liquid that is 0.6 mole fraction octane and 0.4 mole fraction hexane, okay? And we go up here, this is our starting liquid right here. If you draw a straight horizontal line across, then you can see what the vapor of that liquid is once you get the vapor evaporating and you've started distilling this liquid. That vapor is going to be more, contain more hexane and less octane, okay? And so you draw a straight line across. This is the vapor that is directly above that liquid. then you draw a straight line down, and you can look at the mole fraction of that vapor. And so for here, it's 0.69 hexane and 0.31 mole fraction octane. Okay, so it's more enriched in the lower boiling component, which makes sense. When you're boiling something, the thing that has the lesser boiling point is going to boil first, right? So then we've got this liquid of that same composition. Well, it does a distillation, and so then the vapor of that distillation then becomes 0.87 mole fraction hexane, 0.13 mole fraction octane. And so then that liquid condenses. If that liquid does a distillation, then again we clean it up more into where it's almost pure hexane, and then we get all the way over to here, we eventually get just pure hexane. Okay? And so all these mini simple distillations as they're going up the column are purifying that liquid to make it more all one component. All right? So if you look at what's actually happening in this fractionating column, so here is our initial liquid right here. That was the 60 mole percent octane, 40 mole percent hexane. You get it distilling, its vapor becomes 31 mole percent octane, 69% hexane. Then that condenses and forms a liquid, and then that liquid forms a vapor that then becomes 13 mole percent octane, 87 mole percent hexane. And you go up, and we get to 4 mole percent octane, 96 mole percent hexane, and then we get 2 mole percent octane, 98 mole percent hexane. So we just have 4 sets of distillations here, and as we go up, we purify that hexane more and more. So as you climb a fractionating column, the boiling point of that liquid as you go up is going to decrease as you go up because you're purifying more of the lower boiling component. Okay? And then once you get rid of the lower boiling component, then you're going to purify the next highest boiling component. Okay? So does everyone see how that works? Okay. So each of these is considered a theoretical plate, as well as here, we're looking at all these steps are theoretical plates. Okay? So possibilities for fractionating columns or fractional distillation columns. You can buy this column here, letter A. It's called a Vigoro column. So you can buy columns that are fully intended for doing fractional distillations. These guys are really, really expensive, okay, and they get broken very easily because of all these little plates inside. So we're not going to put these in student drawers because you don't want to have to pay for it if something happens to it, okay? But instead of using something like this, we can just take our Liebig condenser and put things in it. So we could put glass beads in it and put a little bit of steel sponge at the bottom to hold all the glass beads in. Or we can fill the whole thing with steel sponge, which is what we're going to do this week to add more theoretical plates to our distillation and help you purify your unknowns. Okay? And so this is what your setup for this week is going to look like, okay? This is figure 4.7 from your lab manual. I'm just going to go through some specifics here and some things to keep an eye on as you are setting it up, okay? So first of all, I would set this up over your stir hot plate. You want to be able to stir your mixture, so you want to have a stir bar in there. So have your ring stand, have your stir hot plate. Then you're going to start with your 100 milliliter round bottom flask. The reason we're starting with that is we have a 100 milliliter heating mantle, so the two of them go together well, okay? So you want to make sure that your round bottom flask is clean and dry. Now another thing you have to be careful of, you can't use acetone on the interior of any glassware to clean it this week because acetone will give you a false positive test for an alkene, and that's one of the things you're going to be testing for. Okay, so you can't clean anything on the insides with acetone, all right? So make sure things are as clean as possible, dry them out as well as you can, okay? Then what you're going to do is first clamp your round bottom flask. This is very important. You want that flask clamped nice and vertical, because for the fractional distillation you want things very nice and vertical for the fractionating column. It'll work a lot better if it's straight up and down than tilted to one side or the other, right? Then you're going to clamp that live bait condenser, okay? And before you put that condenser on, you stuffed it with steel sponge, which we'll show you in lab this week how to do that. When you're stuffing it with the steel sponge, you have to be careful. There's some little prongs in here that are easily broken. If they break, they ruin the condenser. So be really careful when you're putting the steel sponge in there not to break the prongs, okay? The jacket of the condenser you also want to be free of water, because as you're heating your liquid and it's boiling and condensing in this column, you don't want heat expended to actually dry out and vaporize water in your column, okay? So the outer jacket of the column, you can use acetone on the outer jacket, rinse it out with acetone, and then connect one end of it to your vacuum line in your hood, okay? Put a piece of black tubing on it, connect it to the vacuum, and it'll help blow out your condenser so that it's completely dry, all right? Then you've got it clamped nice and vertically, and on either the bottom or the top, you're going to put your pipette bulb. The reason for that is we don't want any convection, we don't want any circulation of air going on in the condenser, because that's going to fight your fractional distillation as well, okay? So we want to stop that airflow by closing off one end. So you put your pipette bulb on one end, that'll take care of it. And it doesn't matter if it's the bottom or the top, okay? Then you're going to put your three-way adapter and your thermometer. It is very important, your thermometer placement, okay? You will be determining what your unknown is based on its boiling point, and you need to be able to get a very good, very accurate boiling point range. So make sure the tip of that thermometer is just under the arm here of your three-way adapter, okay? Make sure that you are getting accurate boiling point temperatures as this distillation is going on. Otherwise, if you don't have good boiling points, you won't be able to figure out what you have, okay? So it's the boiling points and chemical tests is how you will figure out what you have. Then you're going to come down, you're going to use your West condenser. So your skinny condenser, make sure that's attached tightly, water in always on the bottom, water out on top. So no water here. Water is going to go on the more horizontal condenser, not on the vertical, okay? Then you'll have your vacuum adapter. Then you're going to use test tubes to collect fractions from your distillation, okay? Or sorry, not test tubes, graduated cylinders. So you want your 25 milliliter graduated cylinder and your 10 milliliter graduated cylinder need to be clean and dry. And you're going to be exchanging between the two of them as you're collecting different fractions so that you can measure the volume of them. Be really, really careful not to take the base of the graduated cylinder off. It is a real temptation because you think you can read the volume better that way. But when you go to set it down on the bench, it's really easy for it to tip over. And so you could do the whole fractional distillation, set it down on the bench, have your fractions spill all over your bench, okay? So don't take that base off of there. Also, when you're clamping on graduated cylinder, be careful. A lot of the vacuum adapters have this little tip that goes down below the adapter. So when you're exchanging grad cylinders out from each other, in and out, you don't want to clip off that tip, okay? So be careful how you clamp things, and be careful when you are exchanging things. First lower the graduated cylinder and then pull it away and put the new one in place, all right? Okay. The other thing is just make sure all of your joints are completely tight. Use a little bit of vacuum grease. Make sure everything is sealed throughout, because you don't want to be distilling here and lose it out of joint here or lose it out of joint here and not be collecting temperature versus volume, because what you're going to plot in the end is the temperature versus the volume that you collect. So you need it over here. You also need it for the chemical tests, okay? Questions with the setup? Okay, and we have, just like all of the previous weeks, we have them set up in the lab, and we will show you in lab how to set it up. Okay. Now, one thing you want to do, you're going to use your heating mantle for heating things, but you all have different unknowns. So I can't say, turn your Ohmite to setting whatever, and it's going to work for everybody. It won't, okay? So you're just going to have to turn on your Ohmite and very carefully be raising the voltage on it as you're paying attention to what's going on with the distillation, okay? So you want to keep adding more and more heat till you've got a nice distillation going. Then you're probably going to have a little bit of a drop, and then, or maybe just a rise in temperature. Then you want to up the Ohmite setting more, get a nice steady distillation going, okay? So you want 2 nice steady distillations, and you have to be vigilant on your Ohmite, but not go crazy, okay? So you don't want to start at a setting of 80 because it's really easy to overshoot your low boiling component, okay? So I'd probably start to where you just start feeling heat at the heating mantle, and then just very carefully but vigilantly. This shouldn't take all 5 hours to do the distillation, so that's why you have to stay on it, but not overshoot it, turning up the voltage on your Ohmite, okay, for your distillation, all right? And so in the end, this is what you want, okay? We're going to get a distillation curve where we're going to plot temperature and cumulative volume, and from this we'll be able to figure out what our lower boiling component is and its boiling point range, and our higher boiling component, okay? And we want to isolate these two, and we want to maximize the volume that we get for each of these, okay? The other thing I would do to help with this is make sure that you are taking volume readings every half a milliliter or less, okay? So you want to read for every volume that's collected. You're going to also read a temperature. You want to read that at least every half a milliliter that's collected, if not sooner than that, all right? The more data points you get on this graph, and in the end you're going to make a graph like this. The more data points you get on this graph, the better you will have, better results you will have from the fractional distillation, and the easier time you will have figuring things out, okay? So you don't want to have huge gaps where you don't have data points, because then it's hard to tell, did it go up? Did it stay the same there? What am I going to do with that fraction, all right? So what you are going to do is, first of all, before you start heating anything, before you have anything checked, okay? You want to have 6 small vials, clean and dry. Okay. And those are on the center shelves in the lab. There's boxes of vials. You just want 6 of the small ones, the 7 milliliter ones, and you want them clean and dry. And hopefully that's more than you need, but you at least want more than you need, then decide you need more than you have and have to be scrambling in the middle of the distillation, okay? So you may not use all 6, but that way you're prepared. The other thing, and again, in these vials, no acetone, okay? So do not clean these guys with acetone. You also want them dried out, so you don't want any water in them, okay? So we're making things a little bit tricky for you guys this week. The other thing that you want is this table that I am going to draw here on the board. You want that in your notebook, probably on a full notebook page so that you have plenty of space to fill in the table. You want this table put together before you start heating and collecting any fractions, okay? So you're going to have, in this table, you're going to have a temperature column for temperature. You're going to have a column for the volume collected per fraction. It's going to be in milliliters. You're going to have cumulative volume. to have your observations. Now, one thing that is really key to all this is observations, and a lot of times what people forget to do in all this, they're so worried about getting temperature and volume and getting their whole table collected, you don't get any observations. So make sure that you do include observations. Tell when you change the ohmite setting. Tell when things started boiling. Tell when the temperature started dropping. Write down when the temperature starts increasing. Put all these observations in this table, okay? Because you are also graded on this column. And you can't do a fractional distillation and not have any observations at the end. There should have been observations made, okay? So don't neglect that column. So for this distillation, say we're collecting temperatures here, we're going at least every half milliliter. And so for this volume collected per fraction, this is just going to be the volume for each individual fraction. Okay, so say, first temperature, we've got a milliliter, and then 1.5 milliliters, and then 2.0 milliliters. And then we switch graduated cylinders. So we decide right here, something's happened with the temperature, we need to switch graduated cylinders. So we take this temperature reading, nothing's been collected. Then we have another half a milliliter is collected, and we take that temperature reading. So every time you switch fractions, you're going to start this column over, okay? This is going to be the volume for each particular fraction. So you're going to read what that volume is in the graduated cylinder that you are collecting, right? Then for cumulative volume, we want these to keep going. We don't want them stopping as you collect each fraction, okay? So it'll start out the same. But then you keep adding. Okay, so does everybody see how that works? Okay. In this table, make sure it's very clear where you're changing out your graduated cylinder, so you can put a dashed line in between. But also in the observations part, make sure you put that you've changed the graduated cylinder. Make sure if you've changed the heating setting that you put that. Make sure you give the initial heating setting. Okay. So in this observation side, make sure all that information is filled out. So when we go to look at your notebooks, we want to be able to see clearly from your table what happened with your distillation, okay, and where things were changed out. And so in the end, from this table is where you're going to come up with this graph, all right? And in your notebooks this week, right after you finish the distillation, you want to put a rough draft of your of this graph in your notebook itself. That way you can figure out what fractions you want to test with the chemical test, right? Then for experiment 4, I'm going to show you in a little bit, there's going to be report sheets that you hand in as well. Part of that report sheet is a nice drawn or Excel drawn, nicely computer generated nice graph. You want to include that on your report sheets, okay? But in lab this week, we don't expect that you get a nice Excel drawn graph. We just want you to put a rough draft in your notebook, all right? For either graph, make sure that you do show all your data points, okay? So if you're using Excel to graph it, when you make your nice graph, make sure you use a scatter plot and make sure it shows all your data points, okay? And then you'll connect your data points. On the graph, you also want to show all the fractions that were collected, so give the labels, if it's fraction 1, 2, 3, fraction A, B, C, D, give all that information on there, okay? Make sure they're clearly labeled. Use the dashed lines that are on here to show where those fractions start and end. You can label things like the forerun. Sometimes you will have liquid that's collected before you get to a steady boiling point. Sometimes you won't. If you have a much lower boiling component, a lot of times you won't have this little bit of volume that's collected in your rise to that boiling point temperature. You'll just start here, okay? So don't be surprised if you don't have a fraction A, but don't be surprised if you do, all right? So be ready for either case, okay? Yep.
Let's problem because we have impurities in our first distillation.
well, that's why we want to like keep collecting fractions. So yes, if you do have impurities, it's going to cause a problem. Same with over here, if you have impurities, it's going to cause a problem, okay? So ideally, you need to watch the temperature and figure out when you're going to be changing your fractions based on the temperature, okay? So you do want a portion that has a nice, even, steady boiling point that you have collected. Then you'll have a mixed fraction in the middle, going up to the higher boiling component. You want a nice, steady boiling point range that you've collected that fraction at, and then you'll probably have the hold-up volume. You won't boil everything away. You don't want to heat your round bottom flask to absolute dryness, so make sure you stop it when there's a little bit of a puddle left in that round bottom flask, okay? One thing I didn't mention on, and we'll show you this week in lab, on your apparatus, you're going to want to have insulation basically from this round bottom flask all the way up into here, all the way to the top of the Liebig condenser, but not really beyond that. That will help keep things insulated so that it will help make it easier to have all these simple distillations occur without heat being given off to the outside. But with that, keep watching, like keep peeking into your round bottom flask and make sure you watch what's going on in there, okay? So you don't want to go to absolute dryness with the distillation, right? So you will have a little bit left, and you will want to measure what that volume of that little bit left is. And so that's what that hold-up volume is. So with the question about impurities, be careful. You want to make things as get as clean fractions as possible. The other thing you want is once you have your clean fractions, don't contaminate them, okay? So once you have your nice clean fractions, keep one pipette for one fraction, another pipette for the other. Don't cross-contaminate. Don't contaminate with vials. Once you've got them separated, keep them separated, because if you cross-contaminate, it's going to make your tests a lot harder, okay? And so there's two tests that we're going to do. The first one is the bromine test. And if you haven't covered this in lecture, you will be covering this reaction shortly, okay? And so this is a Br2 electrophilic addition reaction. And so what we are looking at with these two tests is reactions with alkenes, okay? So one of the components in your unknown will be an alkene. And so we've got our generic alkene here. These compounds are clear and colorless, okay? So you should have a very clear, colorless liquid. Looks like hexane, looks like water. No real color to it, okay? You add bromine to it, and our bromine is in a solution of carbon tetrachloride, so you need to be really careful with it. Use it only in the hood. Don't get any on you. Wear gloves when you're handling it, and you don't want to inhale any of the vapors, okay? So keep everything in the hood. This bromine is kind of a red-orange color. And so if you add it to an alkene, what you are going to see, and once you cover this reaction in lecture, you will see why we add across a double bond the way we do, okay? So the way I'm drawing this is not random. There is a reason for that, and so you'll see that in lecture. When you add bromine across that double bond, this is clear and colorless as well, okay? And so it's kind of funny sometimes to keep track of what's going on. You're starting with clear and colorless, you add red-orange, you end up with clear and colorless if you have an alkene. So the disappearance of this red-orange is a proof of a positive test for the alkene, okay? Especially upon adding a number of drops, okay? Now if you get up to like 25 drops of bromine, you can stop. Like, we don't need to completely quench your alkene. So it tells you in your lab manual you're going to keep adding bromine till you get the persistent red-orange color. If you've added 25 drops, it's going to be pretty evident that you've got an alkene there, okay? So you don't need to keep adding and draining the bottle of bromine just to make sure that you definitely do have an alkene, all right? But it's going to stay clear and colorless as long as it's reacting with the alkene. As soon as you've consumed all the alkene, then it will hold the color of the bromine solution and stay red-orange, okay? But it's only after you've consumed your entire alkene. Now with this reaction, there's another reaction that can occur with bromine, and that's a radical substitution reaction. So again, this time I'm not looking at our alkene, but we're just looking at an alkane, okay? We've got R groups here of our alkane. And then we've got a proton here, or more than one of these R groups can be a proton. We react that with bromine. And we've got this, like I said, it's a solution of carbon tetrachloride. That reacts, this solution reacts with this alkane in the presence of heat or light. And then what you get is a substitution reaction. Okay? And then you also are going to give off HBr gas with this. And so with the bromine test, it tells you after you've added the bromine, you're going to test for the pH of the vapor right above what you're adding the bromine to. It turning red is a possible indication of there being HBr gas that's given off, and so it's reacting with an alkane versus an alkene, okay? Now this reaction is not going to happen as robustly as this reaction, okay? So you may add a few drops of bromine, see it stay colorless, and then after a few more drops, it'll probably hold its bromine color, but you will also probably see this acidic pH paper, okay? Don't let the acidic pH paper be the end-all for your decision of what's going on, okay? So a lot of times people get hung up on just, well, I had red pH paper, it must be an alkane, not an alkene. Take that into account, but look at your overall results. Look at what happened in general, how many drops of bromine did it take? Look at the other test results from the permanganate reaction. Look at what happened with your other fractions, okay? But don't let this evolution of HBr gas or apparent evolution of HBr gas be the end-all for your decision making, right? But this is a possibility, okay? So the other test that you will do is a potassium permanganate test. And in order to have an alkene, you need both tests to be positive, okay? So I've shown you that the bromine test can give you a false positive if it reacts with an alkane. That's why we have two different tests for the alkene, and you want to make sure both tests are positive. So you guys may remember permanganate from Gen Chem lab. It's a nice purple solution. You don't want to get it on yourself because it turns your skin brown. So again, use in the hood and wear gloves so you don't turn yourself brown. Otherwise, if you do turn yourself brown, we know that you weren't wearing gloves. So the permanganate solution is nice purple, eggplant purple colored solution, okay? Again, our alkene is still colorless and clear. If this reacts with an alkene, and the permanganate's made up in a solution of water, then we get a diol. This is colorless as well. However, it also manganese dioxide, which is a brown precipitate. And so you're looking for the formation of this brown precipitate and the loss of the purple color. So this purple color is going to fade, become more towards colorless with the formation of a brown precipitate to result in a positive test, okay? With this test, you want to wait about 3 to 5 minutes to check the results, okay? Sometimes it takes a little bit. So don't look at it, add the permanganate, look at it, and make your decision right then. Let it develop about 3 to 5 minutes and then see what you have. Okay? And with both of these, you need to take into account all of the test information that you have. Okay? So if one of your compounds or both of your compounds gives you 2 positive bromine tests, but the permanganate test is positive for 1 and negative for 1, that may help you out figuring what you've got, okay? Figuring out which one is the alkene and which one is not the alkene, okay? And so we are going to have, in our unknowns, one of them will be an alkene. The other one will be an alkane or an arene. Now granted, an arene does have double bonds, but it's not reactive under these test conditions, okay? So we've got an aromatic ring, but you're not going to see these double bonds will not react with the bromine and the permanganate under these test conditions, right? So one of the unknowns is an alkane or arene. It can be either one, and one of them is an alkene. One of them is lower boiling, one of them is higher boiling. It doesn't matter, the higher boiling can be the alkene, the lower boiling can be the alkene. It doesn't really matter, okay? It's just you've got one of these and one of these, and one's a higher boiling component and one's a lower boiling. Okay? And so if you look in your lab manual, you've got the possibilities of your unknowns. So this table 4.1 is in your lab manual. You've got all the possibilities of what can be in there, all right? And so you've got the boiling point, density, chemical class. This is mainly what you are going to need. So based on boiling point and what happens with the chemical test results, that is how you will identify what your unknown is, okay? And like I said, you have 2 in there, so you're identifying 2 different components. You're going to get, the vial that you get is the same size vial that you use for experiment 1. That holds about 20 milliliters, so you have 20 milliliters of volume to start with. Just make sure, be careful, keep things tightly capped. When you have your fractions that you've collected and they're in vials, keep those tightly capped, because at least one of your unknowns is very volatile, so it's going to evaporate pretty easily, okay? So you don't want to have gone through all the trouble, get a nice fractional distillation completed, and then one of your components has completely evaporated on you, because if you need to get more, it will cost you to get more, okay? So make sure that you do, once you have your unknown, treat it very nicely, keep it capped until you're ready to use it. You're going to measure its volume before you put it in the round bottom flask. And then once you have your fractions collected, treat them very nicely, keep them capped so you don't lose them, okay? And don't contaminate them. So what you are going to hand in for this experiment, and it will be up to your professor's discretion whether or not your notebook is added in as well. A lot of times it is. So make sure you definitely need a pre-lab for this experiment in your notebook before you come to lab this week. The reactions that I've shown you on the board, the bromine test reactions and the permanganate reaction, is your reactions the list that I just gave you of possible unknowns is your physical data table, basically, except for what you need for the bromine test and the permanganate test. And then for your report sheet, it's double-sided, so you have information to complete about the low boiling component, information to complete about the high boiling component. And then on the back side, you're going to draw or attach your graph. Computer-generated graph is probably best. And then you'll answer questions, okay? Under the data analysis on page 418, this question was stumped a lot of people last year, so I want to go over it for you. In this question, you are looking at the relative percentages or the ratio of unknowns that were in your original mixture. Okay? But you're looking at it based on the volumes you collected of your two purified components. Okay? So you're going to take the volume of the two purified components, add them together, and then take the volume of each one divided by that total and figure out what that percentage is. Okay? So you're just looking at the relative percentage or ratio of what you collected. Okay? And that should be representative of what was in your unknown when you started. All right. Then you will be, and on each of these you want to show your calculations. Then you're going to go through and figure out how much unknown was collected in all fractions and how much pure product for the low boiling component was collected versus original unknown, how much pure high boiling component was collected versus original unknown volume. Okay. Then on the bottom is information for your conclusion. So you're going to attach a conclusion to this, a lot like you wrote for experiment 1 and a lot like what you're going to write for experiment 3. Okay? But you need to address these points in that conclusion. All right? So make sure you're not going to obviously write your conclusion down here. You're going to attach it word processed to this worksheet. All right? And so you'll at least hand in this worksheet and your conclusion and probably also your notebook just for people, your lab prof, to look it over. Okay, so make sure you keep it up to date, all the experimentals in there, pre-labs in there, all your signatures are in there. Okay. One thing I want to mention as far as lab notebooks that I saw, at least with my classes that I graded, not everybody is getting signatures when they are working in open lab. Make sure you get the signatures from the person that is in the stock room when you work in open lab. So every time you are in the lab, you should be getting a signature, okay? The other thing I want to mention about lab is it was kind of a pigsty this afternoon. So everybody doing their melting points, getting their weights, everybody is not clean up after themselves, okay? So make sure that you do. Otherwise, what you can do is take away open lab time and just expect you to take care of it during your lab period, okay? So keep the labs neat and tidy.